So we are continuing our series here on applying Gauss's law to slightly more advanced geometries than we did in general physics. And we had already laid out the basic case for when we have plane symmetries. And now we want to look at some additional examples. Now again, the sheet of charge that we had done back in general physics, I'll just remind you of that real quick in terms of what we found. That we ended up having an electric field. Let's get rid of that. The electric field was given by the surface charge density over 2 epsilon naught. I'm not going to show how we got that again. Go back and look at those other examples. So now we're going to talk more about a slab of charge. And for these ones, we are going to use the geometry that the charge is contained sort of in the XY plane. And that the direction that we're measuring it relative to is going to be the z-axis. It doesn't really matter if it's x, y, or z. It's just recognizing that the direction we have to integrate over is going to be the direction perpendicular to the slab. Okay, so we're going to first just talk about, again, the setup real quick. Our Gaussian is some pillbox which is either outside or inside the sheet, but centered symmetrically on the sheet. And what we saw was, as long as it is symmetric, we expect that we're going to have the same electric field, equal distances on both sides. And so we can change our integral of the E dot dA is going to become that magnitude of the electric field and 2 times the area of the Gaussian, 1 for the top and 1 for the bottom. And this is true whether we're on the inside or the outside, as long as we're sort of symmetric in here. The electric field's going to be the same on both sides. And so, since this is the left-hand side of the Gaussian, the right-hand side of the Gaussian is the charge enclosed over epsilon naught. And we find that the electric field is equal to Q enclosed over sigma naught 2 times the area of the Gaussian. Like most of the problems that we've been dealing with, it's finding that Q enclosed that we have to worry about. So for this plane symmetry, if I've got a volume charge density, it's going to be the integral over that charge density, which will go to the integral of rho d tau. And we're going to separate this out to be an integral of rho dx, dy, and dz. Now, just to make things clear so we can sort of see what's happening here, we're going to assume that our Gaussian is some x a y b and some z that's going to go sort of a distance c. Now, I could center this all on the origin, but it turns out I don't really have to. I'm just going to show you really quick here that if it's centered on the origin, it's going to go from some like minus a over 2 to some plus a over 2, some minus b over 2 to some plus b over 2. And some minus c over 2 to some plus c over 2. And we've already said for symmetry that rho could be a function of z. But not rho as a function of x and y. We have to have it symmetric across the plane. Well, that means we can get our Q enclosed here, and it's separable. I've got the integral minus c over 2 to plus c over 2, some rho which could vary with respect to z, dz. But then separately, I can do the integral over the x and y coordinates no, that's dx. And this one is just going to simplify down to a. This one is just going to simplify down to b. And this is the one where we need to actually do the integral. But I'm going to take just a little bit more time on this general setup to show you then that what we've got here, if I just cut and paste this, this is going to be equal to my A times my B times the integral of rho dz all over epsilon naught 2, but the area of the Gaussian surface is AB. Because it's the xy part. And so this simplifies down to give us this integral of rho dz over 2 epsilon naught. Now, if I compare this to my flat sheet, where the electric field was equal to sigma over 2 epsilon naught, it would seem like for the thick sheet, that the integral of rho dz is sort of an equivalent surface charge density. Now, when I was looking up some other resources for this, they actually called this a sigma, not as in the summation sigma, but the integral of my rho dz is an equivalent. You could also, I suppose, call it just explicitly sigma equivalent. Now, in this video, I'm going to do the uniform density case. And then we'll talk about some other possible cases. So here, for this case, when I say uniform density, what I mean is rho is a constant. It's going to have some units of coulombs per meter cubed, and it's just going to be a value. Well, for this, I need to then do the integral. But I have to look at it in terms of different regions. When I'm outside the slab, rho is equal to that constant value just inside the slab. So when I do my integral of my rho dz, I'm just going to do it from minus c over 2 to plus c over 2. Since rho is a constant, it comes out. The integral of dz is just z, evaluated from plus c over 2 to minus c over 2. And so that's rho times plus c over 2 minus a negative c over 2, which just gives us a value of rho times c. Now, going back to my Q enclosed, well, that was my A times B times the integral of the rho dz. And so it's rho times A times B times C, which makes sense because that's rho times the volume. And so if I've got so much charge per cubic meter and I know the volume of my slab, I can find out the total amount of charge. So my electric field here again is going to be rho c over 2 epsilon naught outside the slab. But then if I'm going inside the slab, I only care about the charge inside, and so that's going to go from minus z to plus z, where z is less than c over 2. And so my integral is going to go from minus z to plus z rho dz, which again is going to be rho z evaluated from plus z to minus z. And so that's rho plus z minus negative z. Which is rho to z. And my electric field is then rho 2z over 2 epsilon naught, which is rho z over epsilon naught. So this is the outside and this is the inside. Okay. Now, I will further just mention here that because this can be thought of as our equivalent surface charge density, this is still the equivalent charge density over 2 epsilon naught. But now where the equivalent charge density is just for the charge inside my Gaussian. So it's less than the full surface charge density. Now I'm going to stop this video here for a minute.